student from Northwestern Polytechnical University of China. I appreciate the opportunity to use this video to present my work at the conference. I am under the guidance of Professor Ma Binghe. Our team have made achievements in variety of sensors. We used MEMS technology to manufacture hot film shear stress sensors, studied structural design, annealing, and calibration, and applied to boundary layer transition detection. My major focus on developing flexible sensors to measure fluid parameters such as shear stress, pressure, and temperature, and make them more accurate and reliable. Today, I would like to introduce you about my latest research on hot film shear stress sensor, which is the influence of size effect on the dynamic characteristics of hot film shear stress sensor. This work was supported by the National Natural Science Foundation of China, completed in the K Laboratory of Micro and Nano System for Aerospace, Ministry of Education. As we all know, turbulent boundary layer is one of the core issues of modern fluid mechanics. With the progress of experimental technology, it is found that typical vortex structure exists in flow field, which plays an important role in the generation, maintenance, and evolution of turbulence. Shear stress is an important basis for judging the state of boundary layer and studying the evolution of vortex structure. Despite significant progress in turbulence measurements using particle image velocimetry means PIV and laser Doppler velocimetry means LDV in recent years, hot mirrors and hot films remains the main devices for measuring energy spectrum and energy dissipation in turbulence measurements in gas flow because of their high spatial resolution and response. Compared with other shear stress sensors, the hot film sensor based on of phosphate into boundary layer with less interference to the flow field. There are several ways to measure the dynamic response. The most direct way is to continuously changing flow, such as using a shock tube. Frequency response is obtained by taking the inverse of characteristic time, but this condition is difficult to create and capture, so the sonic strobe and the plane wave tube are used to measure the dynamic response. Alternatively, the square wave test was proposed by famous and proved to be simple and effective. We also use this method. Improving the dynamic characteristic of hot film sensor can extract more effective information from the flow field, which is helpful for precision measurement of turbulence. Several methods have been proposed, such as processing vacuum cavity or heating via under the method of heat dissipation includes heat conduction, heat conversion, and heat radiation. As a constant thermistor to the operating temperature is a dynamic process in which there will be heat accumulation. The flow generates shear stress, which acts on the hot film sensor to form a temperature gradient. In constant temperature drive mode, the feedback circuit readjusts the drive current so that the thermistor maintains a constant temperature. In this way, we can know the shear stress by measuring the voltage of the thermistor. Four kinds of heat dissipation can be described by the following formulas, respectively. We finally obtain the relationship between total thermal power and the size of the thermistor, which will be further verified by experiments. Four kinds of hot film sensors are designed with the same aspect ratio: 1.2 mm length, 1.8 mm length, 3 mm length, and 6 mm length. This is the process for fabricating hot film sensors. Firstly, a layer of 30 micrometers polyimide was coated and cured on glass wafer as a flexible substrate for hot film sensor. Secondly, a layer of 1 micrometer nickel was deposited on the polyimide layer, and then the thermistor and its leads were patterned with photolithography, and finally, release the flexible sensor from the glass. The parameters of spin coating and thermoimidization of polyimide have been studied to produce flexible substrates with excellent properties. We also studied the temperature coefficient of resistance, means TCR, annealed at different temperatures and times. High TCR can improve the sensitivity effectively. Now we are able to achieve the TCR of 5,100 ppm per degree centigrade for nickel thermistors, which is the highest of its type. The experiment of frequency response and sensitivity is carried out in the rectangular microchannel, whose cross-section length is 30 mm and height is 1.88 mm. The flow field is fully developed to form Poisson flow, whose flow state is laminar flow and velocity distribution is parabolic. We can calculate the voltage stretch from the pressure gradient. The digital pressure scanning valve is used to measure pressure gradient. We use 1010 mini CTA to drive the hot film sensor. Square wave position is applied to the bridge. The output waveform is displayed by Angelant's DSOX oscilloscope. Adjust the frequency and amplitude of square wave until the output waveform achieves optimal response. The sensitivity of hot film sensor is obtained by static calibration. The Davisov series equation system, instead of the oscilloscope, is used for sensitivity test, and the square wave is no longer applied. As shown in the first diagram, the optimal response of hot film sensor square wave test is the waveform with slope, and the maximum value of slope is 25% of mean pulse. The span of the mean pulse is the time constant. At the same overheating ratio, the heat capacity decreases with the decrease of sensor size, resulting in a smaller time constant. The frequency response is the inverse of time constant. The second diagram shows that the frequency response has a good linear relationship with the convective heat transfer area, which is consistent with the theoretical equation. We also analyze the time-frequency characteristics of the sensors. It can be seen from their power spectral density distribution that the larger sensor size contains higher energy, but the larger size of the sensor has no obvious perception of the high-frequency vortex in the flow, resulting in the rapid attenuation of the energy contained in higher frequency bands. The above four figures are the calibration curve of the sensors at different overheating ratios, whose slope is sensitivity. A larger thermistor can store more heat and respond to more voltage changes as the flow field changes. Thus, the larger the size, the higher the sensitivity. The increase of overheat ratio can enhance the convective heat transfer rate of the sensor, and its sensitivity will also increase. At the same overheat ratio, the sensitivity and the convective heat transfer area do not follow a linear relationship. Larger size will increase heat conduction and natural convection heat transfer rate, resulting in the limited increment of forced convection heat transfer. Once again, I would like to thank you for the opportunity to present my work. I hope you will give me your comments and suggestions by email. That will help me improve my work. Have a good day and thank you for your attention.